Thank you very much. And also thank you for the invitation to give a talk here. I'm going to talk about apparent horizons and their ultimate fate in these binary black hole mergers. And this is a project that I've done together with Ivan Booth and Roby Henniger. And actually, in the beginning of the project, we just thought we have a easy idea, simple idea. Actually, Ivan and Roby had the idea to find apparent horizons without initial guesses. And it will become clear what I mean with this in the course of the talk. And then we just wanted to apply to numerical relativity simulations of head-on collisions and see what we get. But during the course of the project, our results got more and more interesting. And in the end, we now believe that we can answer a quite old question of how two black holes exactly become one in terms of their apparent horizons. Okay, now let me give an introduction what are actually apparent horizons. I will give a very brief historical overview. Apparent horizons are actually trapped surfaces, which are sort of the progenitors of this concept. They were already introduced in the 1960s by Penrose, and we've heard the term of trapped surfaces already in Vitor's talk. And these are basically introduced in the context of the singularity theorem, the first one that Penrose published in 1965 here. Here's a screenshot of that famous PRL. And a trapped surface is just a surface, a smooth closed surface where light rays emitted to the outside and to the inside converge in both directions. That's something that cannot happen in flat space for a closed surface. But in curved space, that's possible. And he showed essentially, well, the simplified version of that theorem is that if there is a trapped surface in space-time, then you're also going to have a black hole. The concept of a trapped surface was then slightly generalized by Hawking to trapped regions and marginally outer trapped surfaces and apparent horizons, and all these depend on each other, and I will introduce their definition in a little bit. But this all only exists in individual slices, individual time slices, so instances of time for some notion of time. The time evolution of these surfaces was then introduced by Hayward and in a concept he called trapping horizons, which was the inspiration for Ashtekar, Krishnan, and others to develop the full mathematical framework of what is called the quasi-local horizon paradigm. And in this framework, black holes are modeled using isolated horizons when they are in equilibrium and dynamical horizons when they are interacting. And so these quasi-local horizons, of which MOTSes are an integral part, they are used in numerical relativity every day. Whenever you do some numerical simulations of black holes, you always take a look at these MOTSes to find out whether you have black holes and what their properties are, mass and spin, etc. So on a little bit more technical side, the condition that a surface is a MOTS can be simplified or simply stated as having vanishing outward expansion. So this is the condition for a smooth closed space-like surface to be a MOTS. And the intuitive notion again is if the expansion is positive, then light rays diverge to the outside direction. If it's negative, light rays converge. And if you're just in the marginal case that the light rays neither diverge nor converge, then you have a MOTS. And whenever you have multiple of these MOTSes, one contained within another, for instance, then you just call the outermost one the apparent horizon. That's the numerical relativist's definition of an apparent horizon. And here you have an example of two MOTSes, and these are the outermost ones. So actually the apparent horizon has two components here, and we talk about two apparent horizons. And what I will do on my slides now is that I just cut them open and draw these as these circle-like shapes. And whenever you see such a closed curve on my slides, then you always have to imagine that it's actually a full surface, not just a curve. This has the advantage that we can visualize the time evolution of these here in this upward direction, time running upward, and have these tubes. These are the marginally outer trapped tubes. And what you see here is actually already a simulation where two black holes merge head-on. The fact that these tubes seem to become smaller towards the end is just a coordinate effect of the simulation. The tubes actually, or the individual mods, have non-decreasing area here. And any numerical relativist having dealt with black hole mergers already knows what happens here. The merger happens like this. At some point, you just have a new common horizon that forms seemingly out of nowhere during the course of the evolution when the original horizons get sufficiently close. And then what you do is that you usually just take a look at the outer horizon and don't resolve the interior very much, because also it's numerically very challenging to resolve the interior here. So what we do know is that there is an inner branch of this outer horizon, but not much more was known. So what I will do next is that I show what we found out with our new method of resolving horizons in this interior. And then, as we will see, this resolution of the fate of these individual horizons here will open up more questions, I guess, than it answers. And then we will take a look at these questions and how to make sense of the results. So first of all, I will show a little movie how black holes merge in numerical relativity in terms of these apparent horizons in general. So not yet containing the full history, because that's going to clutter too much the screen. So what you see on the left side is the area of these various surfaces that we track in time. And on the right side, you'll see the shapes. And that's about as far as we could resolve these previously. The individual horizons S2 and S1 of an unequal mass head-on merger here, starting with Brillenquist initial conditions, for those who know what kind of initial data this means. And we see the common horizons forming. I can go a little bit back here. So they form as one surface and then bifurcate into two surfaces here. Okay, now I will focus on just this individual mods here and show only what its fate means, or how its fate is computed in our case here. So this is our result. I'm not drawing the common horizons here, and we see very, I would say, weird shapes forming. And now we find something we found very interesting. The shapes do annihilate, so we could resolve the interior up to the point where this larger individual horizon is annihilated by some kind of mods. It's really a mods. We checked numerically very carefully that our constraints are not violated too much, and all the surfaces have converged. So these are mods. And what you see is there's multiple mods that seem to, at least intuitively, make no sense. So for instance, here, these very weird shapes, they are certainly not black hole horizons by any means. So we have to take a look at what this means. One thing I have to say here is that our numerical results lose this very complicated shape at this point here where it fades out. And this just has numerical reasons that we understand very well, namely that the shape here gets too close to the puncture region. We are using a moving puncture gauge condition here, which means we can somewhat resolve the interior of the black holes. But when we get too close to the puncture, then this region here is numerically under-resolved. So we lose the mods here for well understood reasons. But otherwise, this is numerically very stable here. And one thing we can do now is, instead of interpreting this whole evolution here as one mods annihilating the other, we can take a look at the four-dimensional space-time picture of these world tubes and see that this is actually just one world tube going back and forth in time. And we can visualize this also in terms of the world tubes. So this is a movie showing the fate of this individual horizon as it weaves its way back and forth in time. And there's actually no reason to believe that this will not continue to weave back and forth further and further. in probably an infinite number of times, and I will show a few indications we have for that. However, one thing that is very clear at this point is that we need to ask the question of what these surfaces mean. Do they have any meaning? Is there any relationship between some surface being a MOTS and it also being interpreted as black hole boundary? And the answer is definitely no. Not every MOTS is a black hole boundary. And we can take a very simple condition, a simple criterion to determine whether MOTS is a black hole boundary or not. And for that, I will introduce the property, the so-called barrier property. I will introduce it intuitively here first, and then show a mathematical way to prove that a MOTS has this property or doesn't have it. And this barrier property can be understood as follows. Let's take a MOTS. This is one of the individual MOTSes, the larger horizon we've already seen. And let's draw a few trapped and untrapped surfaces in its vicinity. So the color coding shows which surfaces are trapped. The darker ones are trapped surfaces and the lighter ones are untrapped surfaces. You see the expansion here on this color scale. And what is clearly visible is that in this picture here, the untrapped surfaces seem to be outside and the trapped surfaces on the inside. And if you can show that every close by untrapped surface lies on the outside and every close by trapped surface lies on the inside, then the MOTS has what we call the barrier property. And in a certain local sense of these close-by surfaces, this is very, very close to Hawking's original notion of apparent horizons, which he defined as the outer boundary of the trapped region. And the trapped region is just the region of space where trapped surfaces can exist. And in a certain local sense, this encapsulates this idea very well of having at least a local boundary of some local trapped region here. Close by here, by the way, has a mathematical definition. It just means that there exists a small neighborhood such that every untrapped surface that lies in this neighborhood has to be on the outside or inside. Now, let's take a look at another MOTS. This is one of which we hope that it's not a black hole horizon. So let's zoom in on this upper part and also draw the shapes of constant expansion here, the trapped and untrapped surfaces. And we see they cross the MOTS multiple times even. So definitely, this MOTS does not have this barrier property. However, it is not really too feasible numerically to check every trapped and untrapped surface in the vicinity to be able to prove this. So we need some mathematical way to determine if a MOTS has this property or not. And we are very fortunate in that respect because there is a strong connection between this notion of a MOTS being a barrier and the notion of MOTS stability. So let me give you the definition of what stability means here. The stability operator was introduced in 2005 by Lars Andersson et al. And it's a linear second order operator, elliptic operator that acts on scalar functions defined on the MOTS. And the interpretation of this operator acting on a function is that let's take a MOTS and deform it in normal direction with psi times the normal. And infinitesimally, this creates a family of surfaces, and this stability operator gives you the variation of the expansion under this deformation. And for us, the most important point, this has many different interpretations, and you can do a lot of things, show stability of time evolution of MOTSes with this, etc. But what we are interested in is the eigenvalue spectrum, the spectrum of eigenvalues of this eigenvalue problem. This can be computed numerically. And the nice thing about the spectrum is that if the principal eigenvalue, which is the eigenvalue with the smallest real part, which is guaranteed to be real, even if the operator is not self-adjoint, if this principal eigenvalue is greater than 0, the MOTS is called strictly stable. And Andersson has proven that the MOTS then has this barrier property. And the converse is also true, that a MOTS that has the barrier property has at least non-negative eigenvalue, non-negative principal eigenvalue. Okay, now what we propose is that we call the physically relevant MOTSes those that are stable, so with a non-negative principal eigenvalue. And that gives you a notion of what we call a dynamical apparent horizon. this encapsulates the idea of an apparent horizon being an outer boundary of a trapped region, and also that of a dynamical horizon, which is the notion of Ashtekar and Krishnan and others of black holes that interact dynamically. And let's see which of the mods that we found in this merger are actually these dynamical apparent horizons. So here's again the picture of the area and the different shapes that we've resolved. And we see that this larger individual mods actually is a dynamical apparent horizon up to the point where it is annihilated. And precisely at the point the principal eigenvalue goes to 0 of this stability operator. And this upper branch here, this horizon-like shape, S2 star, as we call it, has a principal eigenvalue that is smaller than 0. And at the beginning, where it bifurcates with S2 star star, the next higher eigenvalue becomes 0. So we can actually track the eigenvalues of this mods across this whole curve and find that one by one, an eigenvalue becomes negative each time this curve turns around in time. And in our case, you might wonder, these eigenvalues should in general not be real, but we have head-on collisions without any spin. So in our case, this problem mathematically simplifies a little bit, and the spectrum is actually real. And now, since there's an infinite number of positive eigenvalues, each one can go to 0. And so we may really have a situation where this curve goes back and forth, even though the horizon does not exist after some finite time here in the interior region. Okay, now that we've taken a look at the larger individual horizon, let's take a look at the full merger and try to establish the full picture, so to say. And here again, we start with the areas as functions of time of the different horizons. And we can now complete this curve. I don't know if many of you have seen such a picture already. That's the usual thing you see, the outer horizon having larger area than the two individual ones, even larger than the sum of the individual ones. That is related to the area increase theorem. And then we have the inner common branch that has decreasing area initially. And we can now complete this diagram and see that also the outer horizon weaves back and forth in time here, even 1, 2, 3 times turning around. If you adopt this picture of the world cube weaving in time. And we also found a few more mods and even more mods that really go, there's really crazy shapes that we find. But one thing that is important to see is the number of negative stability eigenvalues. If we take a look at the stability analysis here, this upper plot showing the different bifurcations we find, and this lower plot, the different annihilations, we see that the stability eigenvalues really go through 0 relatively smoothly across this bifurcation and the annihilations here. And it's not always the principal eigenvalue. For those surfaces that already start out being unstable, so having multiple negative eigenvalues, it's some of the higher eigenvalues that go through 0. Okay. One thing that you can notice is that all the shapes that are straight lines, so without being dash dotted or anything, they are the ones that have no negative stability eigenvalues. These are the dynamical apparent horizons as we propose, and these are the ones that you already knew from the previous analyses of black hole mergers. So it's a good thing to know that even though there's many more shapes, it's actually the most important ones that were already known previously, and they are also the easiest to find, fortunately. Okay, now what we can do is take a look at the complete merger picture now. And this time I will use colors and line thickness to indicate the stability properties of these mods. So the lighter the colors, the higher the number of negative stability eigenvalues. And what we see is here the different bifurcations of different mods. And then as we move across and go through the whole merger procedure, we see the individual mods touching and then intersecting each other. And here we see the two annihilations that we could resolve. One thing that I did not yet mention is we do have numerical indications that this and this shape, so the ones being there in the very end, they do merge at a much later time, but that's numerically much harder to resolve because of the late time and the surfaces moving again very close to the puncture. But if anyone is interested in our numerical results for that, I can show a few plots there. Now, let me briefly talk about the numerical methods we've developed to resolve this and what I mean with being able to find mods without initial guesses. So first of all, I will give a short overview of our idea of finding mods that are self-intersecting and highly distorted, such as those that we've seen already. And for that, I will introduce the basic idea of how to resolve mods and then how we change it. So the basic idea is that you have a star-shaped mods, at least in your numerical coordinates. So the mods can be represented with a reference point and a distance function. And this distance function depends on, for instance, the two angles theta and phi, if you will. And then the mods condition turns into a nonlinear partial differential equation for this horizon function, which you can use different numerical means to solve. Obviously, this won't work if the mods looks like this, if it's not star-shaped. And our idea is to use a reference surface instead of a reference point and describe the mods with a distance function relative to the reference surface in normal direction here. And that way, the mods condition turns into the same nonlinear problem for the distance function, formally at least. And our code to solve that using a pseudospectral method is public here, although the code currently is only dealing with axisymmetric configurations where the whole mods can be uniquely identified using just a curve, which you can then rotate into the surface. At this point, you may wonder, well, you still need an initial guess. You need the reference surface at least to be able to match the mods. And there's three answers to that. One is if you have a mod from some time during the evolution of a mod. For instance, here, this is the inner common mods, which you can resolve using the traditional star-shaped assumption. When you follow it through time, it provides the perfect reference surfaces for your method. And so we can take the previous time step as reference for the next one, and this way resolve even the highly distorted shapes. However, it gets a little bit more interesting for the cases where you don't know how the mods should look in the first place. And that's how we actually found all these interesting shapes. And the idea here is that we used a generalized shooting method. And the shooting method is based on the following idea. You say that you are in axisymmetry, so the mods that is axisymmetric can be represented just using a curve. And you take the surface of revolution to get the full mods then. And if you formulate the mods condition in terms of just this curve, then you get two coupled second order ODEs, which we call the modsodesic equations, similar to the geodesic equations. And these can simply be integrated. You take some starting point and initial direction, and then you integrate this curve. And if, like in this case here, the curve just travels off to infinity, then this means you have a marginally outer trapped open surface, a MOTOS. You can do some things with this, but it's not going to be a mods. So you wiggle the starting point a little bit until you get a curve that closes upon the symmetry axis, and then you have a mod. And then you can follow this again with our horizon finder that we've developed. That's the first method that describes how we can find mods. Oh, by the way, I said that we don't need an initial guess. That is meant in the following way. If you start with if you want to start with an initial guess, then the shape space of possible initial guesses is infinite dimensional. So you have no chance to just guess all the different shapes there can be. However, in this case, you have just a one-dimensional problem. You just have to scan this one-dimensional line, and then you can get all the different axisymmetric mods that close and have a spherical topology here. The other idea that we've developed is that we start again with the mods in our numerical coordinates. There we need some mods to begin with, but then we can try to use these surfaces of constant expansion and try to generate the full family of surfaces of constant expansion. Like in this lower plot here, this shows the expansion versus the area, or the area versus the expansion in this parametric curve. And we can, if we can follow this curve through the maxima and get back to zero expansion, we have another mods. And incidentally, these two mods are the ones that annihilate in the end. So this way, the mods that merge are also connected via a family of constant expansion surfaces, which is quite interesting, I think. And we can repeat that from this S2 star to S2 star star. And these are the two that bifurcate in the beginning. So this is also a nice way to resolve mods that are connected via one world tube in the evolution. Okay, so to summarize very briefly, I think I've shown that we've developed two new methods of finding unexpected mods without using initial guesses here. And we've seen that these mods participate in bifurcations and annihilations that we've resolved in the interior. More importantly, we've shown that the individual horizons are annihilated independently of each other with horizon-like objects. And still more important, I would say, that the traditionally known mods are the only ones that we should interpret as black hole boundaries. And this is just the three that we found. And okay, if we want to go to full generality, then we now already know what a fully general mods finder has to be able to resolve. And yeah, that's it. Thanks a lot.